I'm going to talking about formal models. So this course is going to be a very rigorous course. So we're going to understand, I don't want to be vague, I want to be very precise. So everything is going to be very precisely defined. So all the intuitions I give today, we're going to make them all very precise. So actually you need both, of course. So you need intuition and rigor. If you only have one, then you're stuck. If you only have intuition, then you can't really reason, you're not going anywhere. If you only have rigor with no intuition, then you're kind of lost because it's very hard to know what direction to go. You need intuition for that. So today I gave you a lot of intuition. So now we're going to get more into the formal aspect, so to make things more precise before we get into the algorithms. So we're going to talk about formal models. Let me just give you just a few minutes to finish today. So basically we want to model distributed systems because distributed systems exist in the real world. The real world is a very complicated place. In real life, things like computers are very complicated things. They use physics to do transistors, all kinds of quantum stuff is going on in there. So it's very complicated. So the model simplifies this, but in a nice way, okay? So the real world is infinitely complex, so we want to simplify this. So we're going to do that for distributed systems. And why do we do that? Well, it's kind of interesting because the real world is infinitely complex, so it's hard to do something for infinite systems. So with the model, we can actually make algorithms. We can also prove correctness, okay, if we have a good model. So modeling is very important. So there's two kinds of models, two major kinds of models, discrete event models and continuous models. So a lot of the courses in engineering, in our engineering faculty, are continuous models, and there's a lot of people who love differential equations. Maybe you took lots of courses where you see lots of differential equations and stuff. Well, in this course we're not going to see any differential equations, so you can be very happy. And no partial differential equations, none of that kind of stuff. We'll be only doing discrete event models. All our models will be discrete, designed by state transition systems and properties of sequences of configuration. So basically, discrete. So that's the nature of computing systems, of distributed systems. So we're going to look at discrete models computing. We're not going to do any kind of continuous modeling at all in this whole course. No differential equation. That's kind of heresy. So the trick is finding the good model. How do you define a distributed system? You can't really define it at the level of physics. That would be too complicated. But you still have to make it powerful. So you have to make it powerful enough that you can actually make impossibility proofs. So powerful enough that actually if something is impossible in the model, it's also impossible in the real world thing. So there's three properties. Actually, the first two are the most important ones. Complete and correctness. So completeness means that if the model, if something is possible in real life, then it's also possible in the model. So whatever can happen in real life, it can happen in the model. Correctness means that if it happens in the model, it also happens in real life. So I don't know, maybe some of you took courses on electronics where we have this thing called SPICE for modeling electric circuits. That's a big problem because sometimes SPICE gives you weird results that don't correspond to reality. So you have to be very careful. So the correctness means that the model, whatever the model does, it's a realistic thing. Okay? It can also happen in the real world. Completeness means that it doesn't miss anything. If it can happen in the real world, you can see it in the model. So we're going to define a model of distributed systems that hopefully is complete and correct, good enough, that will let us do lots of interesting stuff. It's not too complicated, and it's also concise. We don't want it to be too complicated. You can't define everything in terms of quantum physics. That would not be very realistic. Okay? So that's what we're going to do. Last week I gave you introduction. Today I want to talk about what really is a distributed system formally. And then next week, we'll talk about how to define algorithms and stuff, how to specify algorithms, and what kind of notation we will use. So we're going to use a very nice kind of pseudocode, which is actually similar to a language called Erlang, but it's a special kind of pseudocode. It's in the book, and it's very nice for building distributed systems. So with this, we'll be able to make our algorithms in a very nice way. So today we'll talk about formal models. So we gave a little bit of introduction yesterday, last week. So the problem is the real world is very complicated, so we want to simplify it. So the model is going to be a simplification, okay? And modeling is very important. It's what engineers, scientists do all the time. So we're going to make discrete event models for distributed systems and for algorithms. So the problem about modeling is we want the model to be strong enough, but not too complicated. So it has to be complete so that it explains everything that the real world is doing that's interesting for us, nothing is missing, but also correct. It doesn't say wrong things. If it says something, then the real world system is going to do that too. And also, we want it to be concise, not too complicated. Okay, so these are three kind of conflicting requirements. So it's an art to make a good model. So for distributed systems, there's many different ways of doing it. So I'm going to give you a model. It's from a book by Atiyah and Welch. So it's a reasonable model. And we'll see other kinds of models, but this one is kind of a reasonable one that explains everything. So a distributed system, it's a bunch of nodes sending messages and working together to solve a common goal. Okay, that's the intuition. So we want to model that. Okay, so to model that, we're going to start by modeling one node, and then we're going to model many nodes talking together. Okay, so we'll start by modeling one node. So a single node here, it has neighbors, other nodes, it has something computation, and it can send and receive messages between the neighbors. So the single node, we're going to model it kind of like a finite state machine. It's by a model called the state transition system. It's kind of like a finite state machine, except it's not finite, and that there's no input. I mean, the messages are part of it, but there's no specific input. So it's a set of states and rules to go from one state to the other, and starting state. So this is very straightforward for a single node. So here's an example of a state transition system with corresponding to a little program. X is a variable, y of x this and 2, do x is x plus 1, and then x is equal to 1. And so we have states here, which are the values of x. So as the system executes, each execution step, it goes from one state to the next. So we have a bunch of states. So there's a transition function. When we're in the 0 state, the next state will be the 1 state, when it increments x, then the 2, and then it goes back to 1. And the initial state is x0. So it's very simple, huh? The complexity of distributed systems is not here. This is the simple part. Okay, state transition system. The real interesting part comes when we start connecting the nodes together. So let's start connecting them. So in the distributed system, the node is a state machine, but there's also a network. Okay, and we have to model the network in a realistic way. So what we're going to do is we're going to add an in buffer and an out buffer for each neighbor. So if I have a node here, and one with neighbors, 3 neighbors, for example, and 2, and 3, and 4, each of these neighbors, it's going to have an in buffer and an out buffer. in buff and an out buff. And that's going to model the network. Okay? The in buff is the messages coming in, that will be in this set, and the out buff is the messages going out in the network. Okay? So the whole trick is we have to make this in buffer and out buffer work in a way that corresponds to a real network. So you can see already we're going to talk about sets here. So for the first model, we're not going to assume that the messages are ordered. In fact, you cannot assume that for IP on the internet. That TCP has ordered byte stream, but not IP, not the basic one. So we're not going to assume order. And the initial states for these buffers, well, the in buff is going to be empty. Okay, we're going to assume the in buffers are empty. So that means the node actually looks like this. Okay, here's the node, P2, with 3 neighbors, 1, 2, and 3, and it has a local variable x, like in our example. And so there's actually 6 sets that we add. So you see there's a lot of stuff, but most of this is the network. So it starts, they're all empty. So maybe there's a message coming in here. So we have a state transition where the in buffer neighbor 1 gets message M0. And then we have a state transition where we read this incoming message. So the in buffer becomes empty, and we send a message. So the out buffer gets the message, M1, and the state changes to X1. So this is a typical kind of execution. You remove elements from in buffer, and you might, if you send, put things in the out buffer. Okay? So then you can keep going. So here we go to this state here. So for example, there's another incoming message, but the outgoing message is still there, hasn't disappeared yet. So this incoming message, maybe there's even another one. So we have these transitions where we have more and more messages coming in. And then maybe the system now reads the incoming messages, M2 and M3. It does a state transition, and it sends a message on to neighbor 2, M4. So this is the kind of thing the system is going to be doing. So the trick is to understand what these in and out buffs, how they work. Okay? So it's not completely trivial, simple, because the network has some very specific properties. Okay? So for example, the out buffs are kind of special. So all of the states except the out buffs is called accessible state. That means the node can read it, the node sees it. So the node here will see the state and the messages that have arrived. But the out buff is not readable. The state transition function will not see the value of out buff because it's in the network. Okay? So in a real distributed system, when you send a message, the message goes through network protocols and it takes some time to arrive. Once it's been sent, it is no longer accessible by the node. It has left the node. Even on a single computer, it's no longer accessible. If I have a process and I do a send, the message goes into the operating system somewhere, and the network communication layer, and it starts doing all kinds of stuff, and eventually it leaves. And so once you actually do the send, you do not see the message anymore. So the out buffs are inaccessible. So the out buffs is messages in the network. Okay? But the in buffs is messages that have arrived locally. So you can see that it'll be interesting. Sometimes you have to, when I put a message in an out buff on one node, it has to arrive on another node. So there's going to be a transition which is like the message traveling across the network. Okay? That's how it works. So formally, it's a little bit tricky, but it's only because the out buffs are inaccessible. So this is a definition. a formal definition. I give it to you just to make sure that you know precisely what it means, but we're not going to be using it specifically very much, because this definition is basically defining what the in and the out buffs are in the transition. Okay? So the state of a node is a triple. It has a vector of in buffs. So a vector because you have k neighbors. Each of the in buffs is going to be a set of messages. O is a vector of out buffs, and S is the local state, whatever that is. And then you have a transition function, F, which takes one of these triples and makes a new triple. And this is a little bit tricky because this function F, it will read the in buffs, it will read the state, okay? It will empty the in buffs, and it might put messages in the out buffs, but it will not read the out buffs. So O1 and O3 won't read. So we define this function to be deterministic. That means if we have two transitions from here, from triple 1 to triple 2, and f of triple 3 to 4, if these two triples are similar, then the output will be similar. So it's a little bit tricky because of the out buffs. So what we can say, first of all, is that the transition will read the in buffs. So I2 will be empty, and I4 will be also empty. So one thing is the transition function always reads all the messages that have come in. And then it actually does work. If I1 and I3 are the same, and S1 and S3 are the same, then the functions will be the same. Okay, they'll be deterministic. They depend only on I1 and I3. So I put O there because you can actually put messages in the out buffs. So if I1 and I1 is the same as I3, and S1 is the same as S3, then S2 will be the same as S4, independent of O1 and O3. So we're not observing the output channel, okay? It's a deterministic function. So what I'm saying here is the state function transition is deterministic. It depends on the in buffs and the input state only. Okay? And then there is something about these out buffs that we have to say, because the function can add stuff to the out buffs. So first of all, O1 will be a subset of O2. So all the messages that were already in the out buffs in the beginning will still be in the out buffs after the transition, but there might be more messages. Huh? O1 is a subset of O2, and O3 is a subset of O4. So we're only adding messages to the out buffs. Okay? See that? We're only adding messages, and we're adding the same messages. So O2 minus O1, it's the messages we add. And O4 minus O3 is also the messages we add, and these two are the same. Okay? So that means this is a deterministic function. It's saying adding the same messages to the out buff, and it's also not depending on O1 or O3. Okay? We're not using the values of O1 and O3. So this is the little bit tricky formal definition of the state transition function. So it's deterministic. It completely reads the incoming messages, and it might add messages that are outgoing. Okay, so those are the three properties that we formalize here. So the intuition here is not complicated, but because the out buffs have this special property that you cannot read them. Okay, once you put a message in the output, it's in the network, so it disappears. The local transition function does not see it anymore. So that's why we have to define it like this function, okay? Because we're actually storing these out buffs in the model. They're stored at the node, but actually they're in the network and they're traveling towards the neighbor, okay? So this is because of how we model the network. So you see the difference between in buffs and out buffs? You see how it works, huh? The in buffs are emptied and the out buffs are not read, they're inaccessible. Okay, so how does the system actually work? Here? Well, each local node will run a loop. It waits for a message to arrive. Okay, when it receives the message, it does some local computation. Maybe it sends some messages, maybe not, and it goes back to one. So basically each local system is doing something like this. Okay? So this is from the viewpoint of each node, a single node perspective. So what do you think about this model? So let me ask you a question. So this looks like it's deterministic. There's no choice going on here. The state transition function is deterministic. So this is deterministic. Is that reasonable? What do you think? Do we need to make this non-deterministic, or is it okay to have this? Does it model what we want? Are real distributed systems going to be like this, or going to have a deterministic loop? What do you think? Will it be deterministic? Remember that a distributed system...
But is it possible to have a... totally deterministic? Can be possible?
Yeah, that's a good question. Because here we're like assuming that each node is executing in a single thread. No? So that's kind of a limit. But if you have multiple threads reading, they can be like considered to be separate nodes in a sense. Huh? So actually, in a real distributed system, you could have multiple threads. If the message arrives, it could be read by maybe multiple threads. There's actually statements that you can actually do that in a real system. But actually, we don't have to do that. This is an interesting question because of the modeling. Remember, I talked about modeling. Does the model do everything that the real world does? Well, if you have multiple threads of receiving messages, this is not enough, but this is a very simple model. And if you have multiple threads, you could actually have a loop like this for each thread. And then you decide which thread is receiving. So this is actually okay. And I/O, it's also okay, like files and so on. We're not worrying about that here. We're worrying about the distribution aspect here. So that's okay. Atomicity. So when the computation is working here, if a message arrives in the network and I'm in point 2, I will not see that message until I go back to point 1. Okay? Yeah?
So do we consider the messages arrive in the right order? Yeah.
No.
No?
We don't, there's no order constraints on the messages. That's a good point. The system, in the base system is going to be asynchronous, so we don't know how long the messages take. So we really don't know when the message will arrive. So if 2 nodes send a message to a third node, each one of them, 2 messages, we actually don't know which one is going to arrive first. Could be either one. But once a message arrives, during this computation, there's no interruption. Okay? This computation will not be interrupted. We will only treat the second message when local computation is finished. So this operation is atomic. Okay? So is that reasonable? I'm asking you as modelers, is that a reasonable model? What do you think? I mean, computers have interrupts, right? We are not modeling interrupts, it seems, here. Right? Remember, you know interrupts? So is that reasonable to do like that? What do you think?
Who is it supposed to start?
To start?
If everyone is waiting for a message at the beginning, nobody is going to do it.
Okay, that's a good point. That means there has to be a way of adding messages to the system. Okay, sure. So if you only have this, so this is not complete. This is only the execution of the algorithm, it's not the initial state, okay? This is a good point. But what about interrupts? We don't, this is actually an atomic loop. Huh? Atomic, it means that there's no interruption at point 2. Is that reasonable? What do you think? I mean, I'm not trying to trick you, huh? Maybe it's okay. It depends on what you want to model. If you want to model the interrupts, then that's not reasonable. Huh? Maybe you want to model the actual processor interrupt, and that's a kind of low-level complicated thing. But in fact, we don't care about that low level. From this point of view, the local computation is atomic. So if the message comes in during the computation, all that the interrupt does is put the message in a queue, an incoming queue, so that when we come back to 1, we'll see it. So it just handles the message, but it does not actually interrupt this computation, okay? So actually this is reasonable. So conceptually, the computation is atomic here, okay? So this is a restriction, but it's not a strong restriction. It's actually completely reasonable, and it will cover almost all distributed systems, except if we want to really look at how interrupts are implemented, but 99% of the time we don't care. A message comes in, we want to read the message, okay? We don't care how the system is putting it in the incoming queue. That's not in the scope of what we're looking at. So it's perfectly okay to do like this. And that this is deterministic is okay too, because the non-determinism is coming from the message delays, okay? The messages, we don't know which message is coming in first because of the message delay, but once the message comes in, we are doing a deterministic computation. So locally, the computations are deterministic. That's going to be our model. Deterministic and atomic. That's a restriction, but it's not a strong restriction. It's not restricting us in any essential way, but it will help us a lot when we start analyzing the algorithm. It makes things very easy, okay? So it's actually a very reasonable way to model the system, okay? To have this kind of a loop. Okay, so that's enough for one node. Let's look now, we look at many nodes. The first thing I want to talk about is the state of the whole system, of all the nodes. So P1 has its local state, P2 and P3, but the whole system also has a state. Okay? So we're not going to use the word state for the state of the whole system. We're going to use another word for that called configuration. And this is very nice. It avoids a lot of confusion. When I talk about state, it will always be one node. When I say configuration, it'll be the state of the whole system. Okay? So it's a huge difference between those two. Each node here, it's a local computation. It only sees its state. It doesn't see the state of the others. So the nodes do not see the other node's state. So nobody knows the configuration. Seeing the configuration is like what's called a God's eye view of the system. Seeing the whole configuration is not something that a node can do. Okay, the nodes only have local view. They only see local state. So, but we will talk about the configuration when we reason about the system. When we start proving properties, what to behave, see what it's doing, we're going to talk about configurations. So it's easy to remember, huh? State is a small word, it's looking for one node. Configuration is a big word, so it's the whole system. Okay? That's very important to remember, huh? Configuration and state. And then there's an initial configuration where each node is in an initial state. Okay? That's very fine. Now, so we have state, we have configuration. Now we have the execution of the whole system. How does that work? Well, we're going to look at the whole system, the whole configuration as one thing. And we're going to look at the execution as a series of steps. Okay, so we start with C0, which is the initial configuration. So the state of all the nodes, and we're going to do one step here, and this is going to be an event, which I call E0 here. It's going to go to another configuration. So the system is going to execute in terms of events. And there's two kinds of events. There's computation events and delivery events. So in fact, we have this big system with many, many nodes, and all of them are running in parallel, okay? They're all doing stuff simultaneously. We're going to model this as a single sequence, one global sequence of configurations with events. So this is a very abstract thing, because each of these configurations, it's many nodes, and the nodes are running in parallel. So it's actually not so obvious that there's one event which is the first event, okay? So this is actually what's called an interleaving semantics, because we're interleaving the execution of all the nodes. Each node is executing by itself, sending messages, doing local computations. All of that we're going to summarize in a single sequence. So maybe the order can change, Maybe E1 is before E2, or E2 is before E1, so there can be many possible orders. But conceptually, it's as if there's one order. Without loss of generality, we can do that, and this makes it much easier to reason about the system. Easy to reason about, and without loss of generality, because if I have a parallel execution with two nodes running in parallel, with two events, in this execution, I will have different possible executions. Maybe E1 is before E2, or E2 before E1. It doesn't matter because they're independent. Well, in this execution, we're going to model them as a single sequence, okay? And there's only two kinds of events. A computation event, comp I, where we basically are doing local computation. We're applying the transition function f on the node I state. So the node will do its local transition. It will read the inbuffs, it will change its state, and maybe put messages in the outbuffs, send messages. And the other kind of event is one that I haven't mentioned so far. It's called delivery event. Del IJM. This is how you handle communication. This one will actually communicate between two nodes. It moves a message M from the outbuff of PI to the inbuff of PJ. So this is how messages are moving, okay? If I have PI, PJ, I have an outbuff. So outbuff J will contain M. And here we have inbuff I. Starts out by being empty. And when we do a delivery event, we move the message M from the outbuff of PI to the inbuff of PJ. Okay? And this is a single event, so it's considered atomic. So the message, boom, it jumps from PI to PJ in the model. In the real world, a delivery event is not instantaneous. In the model, it's a single atomic event. Okay, the delivery. So you see how we're modeling things here, We're not modeling the event traveling, the message traveling through the system. We will model it to be in the network. So when we put it in the outpuff, it's in the network, and it's invisible to PI. And sometime later, we have a del event, and it arrives. So the del event means that the message has actually arrived at PJ, and it's in the inbuff of PJ. So the del event actually marks the arrival of an event. the out buff, it's in the network, and while it's in the network, it's invisible. And at some point, boom, it becomes visible again at pj. Okay? So this is how we model the sending of a message. We don't actually model the traveling of the message, because that's not relevant from the algorithms that we are looking at. We are doing sends and receives. Okay? So the model will do a send, basically putting in the out buff, and a receive. So the delivery is like a receive. Huh? It atomically moves the message from I to J. Okay? You see that? That's a little bit subtle. This is a typical kind of a modeling decision. Huh? Modeling it this way turns out to be very powerful because it models the essential part. We don't really care about the traveling. That has really no relevance here. We care about messages being sent and messages being received. Okay? So the model models that. And in the execution, it's modeled by a delivery event. And you can see how we now have non-determinism, huh? Because the delivery event, we're not saying when we're doing it. Maybe we do it later on, okay? We put a message in the out buff, but we don't immediately deliver. Maybe we deliver much later, you see? So we actually have a choice when to do this delivery event. It can be very, very late, okay? So the timing, when the message arrives, is not determined. It could be any time in the future, depending on what the model defines. And notice there's no clock time attached to these configurations and events. Huh? There's no time like this is at 3:25.6798 seconds. No, there's no time. This is a conceptual sequence. And it's not possible usually to even put attached times to these events. Okay? So you can see that the model is really abstracting from the real system. Huh? But actually this is a very powerful model. And with this model, we can actually define many very interesting algorithms and prove properties about them. Okay? So this is clear. I'm going to say more about this. Huh? Yeah, question?
It's just about the computation event. When I read the sentence, is there one global transition function, or is it like one for each?
Each node has its own transition function. There's actually a transition connecting data. Comp I is on node I. Yeah? Okay, so we're going to say a little bit more. So this is basically what I just said. So an execution is an infinite sequence of configuration, then I have an event, go to the next configuration, another event, and I have two possible events. A comp event, which applies PI's transition function on I's state. So there's a transition corresponding to this, which we'll see. And the del event moves a message from I's out buff to J's in buff. Okay? So these are the two possible events, and that's all there is. So the executions, all the distributed systems we're going to see in the whole course will obey this model. Okay? So this is a actually very simple model, but extremely powerful, and it somehow encapsulates the really interesting part of a distributed system. Okay? So here's kind of an example. So here we have a system with three nodes, P1, P2, and P3. So they're connected with two net links. So P1 has one neighbor, which is number 1. P2 has P1 and P3 as neighbors, and P3 has one neighbor. So P1 has one out buff, one in buff. P2 has two out buffs and two in buffs. P3 also has one out buff, one in buff. So let's say we have a state configuration in the beginning, where P2 has a state containing M7 in the out buff. And we have a delivery event from 2 to 3 of M7. So the M7 moves to the in buff of P3. Okay? Yeah?
isn't there a problem? Isn't it outbuff 1? So isn't
No, these are vectors. So I'm actually numbering all the in-buffs and outputs sequentially, 1, 2, 3. So P1 has 1 outbuff, P2 has 2 outbuffs, so they're not numbered by the name of the node, huh? It's just their vectors. So each one is just a vector. P2 doesn't know what's at the other end, okay? All that P2 knows is it has a vector of 2 things in there. 1 and 2. It doesn't know what the node is on the other side. So P2 doesn't know about P1 and P3. All it knows is it has these 2 things. So it's just a vector. So this is a del event. So you see it's in one atomic step. It's moving M7 to the in-buff of P3, and it's making it empty here. Right? You see the red part is what changes. So this is atomic. So the network, all of the complicated stuff going on in the network, which you can study in course on network protocols, which my colleague Olivier Bonaventure gives, is summarized by this one step, okay? So we're not going to do more complicated network than that. There's a lot you can say here, right? We're making it very simple, the network here, right? But don't worry, we're going to build lots of interesting algorithms on top of the network. Right? And here's a second event, a comp event. So we're doing computation now on node 3. So it's going to read the in-buff, which is going to become empty on the M7 here. The out-buff, it's going to send a message, M8, which is going through out-buff 1. So it's going to be going to P2. Huh? And then the state is changing to 12. Huh? So this local state has changed, and I'm sending one message. So M8 is in the network now. And later on, hopefully, there's going to be delivery. Yeah?
With del and comp event and functions, how does it know which outbuff or inbuff to check? For example,
the comp event will read all inbuffs. All inbuffs will become empty.
And del?
Del is, the numbers are here, huh?
Yes, but for example, P2 has 2 outbuffs.
Okay, I see. But because it's going to node 3. So from node 2 to 3, it knows it's outbuff 1. Here, the del event is like a global thing, okay? The del event is looking at the configurations. And the message is going from one node to the other. So it's going from node 2 to 3. If you go from node 2 to 3, you see it has to be outbuff 1. Okay? See, yeah, the problem is there's actually 2 views. There's a global view and local view. The nodes are local, but the del event is a global thing. It's part of the execution of the whole system. So we don't care in the del what is the number of the outbuff in the vector, okay? We care about the node here. But there's no ambiguity, huh? Okay? It's the difference between state and configuration again. So eventually we're going to be talking mostly about configurations, huh? What's happening internally in the nodes, at some point it's not so interesting. This is going to be what we're mostly talking about in the course, okay? Okay? So this is an example of how a system is going to be executing. So it's pretty clear, huh? It's very precise. You see how the network is modeled? So the complicated network, look at, even you can do a huge amount of stuff behind the del. Look at multipath TCP, or even TCP, which is doing ordering. Or even IP, which is doing non-trivial kinds of routing, best effort delivery packets. Here, we're all abstracting that away. Yeah? We have a message, which is atomically arriving. Ooh. Of course, the message might be lost. We will model also later on message loss, and we will model reliable delivery. We can also model routing. We can do all kinds of things. But here we have just a neighbor-to-neighbor connection with an atomic transition. That's it, okay? But that's very general, and it's expressive enough that it covers most of the interesting things that distributed systems are going to do, that we're going to talk about in this course. Plenty of good stuff. Okay? So, I want to be a little bit more precise. So, a comp is actually transition connected to it. Huh? So, the I actually doesn't give all the information. There's actually a triple here. A triple, which is S1, S2, I, which is the beginning state, the ending state, and the node. So the full information is actually given in this transition, okay? So a comp event is associated with transition, where we look at the internal state of the node. Huh? Here, we're looking at it at a very high level. We're only saying something is happening on node I. But in fact, there's a transition going on at that node with an input and an output state. Okay? And this transition is applicable in the configuration. So basically, the inputs, the state of J here, S1, S2, J, the accessible state of node J will be S1. Okay? So this transition, if we apply it in a configuration, it means that the S1 is actually what is sitting in node J. Yeah? So there's actually some constraint here. So the comp event will only work, let's say I'm doing S1, S2, J here. The comp event E0 will only work if the node J actually has S1 here. Huh? And the same for delivery. If I do deliver IJM, this will only work in E1 if C1, if the I node really does have M in the output. Otherwise, it's like a mismatch, okay? So these events, it's not just random things. They're actually tightly connected to configuration. I can't just do anything here. I have to do something that works on the configuration, okay? So the sequence of events, they have to be applicable events. This is important because we're going to talk about these events separately. We're going to talk about this sequence. This sequence of events, we're going to talk about that. And this is actually called the schedule of the system. But you can't just put any old random events in there. The events actually have to fit with the configurations. So all the events have to be applicable. Okay? It's kind of a consistency constraint, if you want. If we don't do that, then the schedule is like mistake. It's wrong. It doesn't work with this system. Huh? So all the events have to be applicable. So here's another example. What I want to do is make the connection between the comp event and the transition. So here we have a very simple system with two nodes, P1 and P2 with a single connection. So P2 here has M7 in its in-buff. It's going to read that event, do a transition. So the in-buff is empty here. It's going to send M8. So it's going to put M8 here, change the state to 12. So this actually corresponds to a transition. Okay? Here we have the accessible state here. So the in-buff here is M7. The X is 11. So this is the input state. The output state, here we're actually adding M8 to the out-buff. And the X12 and the in-buff is empty. Okay? So here notice that we're looking only at the accessible state. We don't care what the outbuff is here on the left. Because the outbuff is what's in the network. It's invisible to P2. So here it's empty, but in fact P2 doesn't know what's here, what's in there. It's what's in the network. Okay, so comp events correspond to transitions, and the state here is the accessible state of the node I. Okay? Those all just details to make sure that everything fits together in the model. Okay, and then we can define little functions. We have this little function called apply, or apply. So if we apply event E to configuration C, it gives the next configuration. So we can say something like app of E0, C0 will be C1 here. So apply is basically the function that gives us the next configuration if we give the event. So app of E1, C1 will give C2, and so on. So we can actually define this step as a function. It's just to have a notation. Sometimes it's nice to talk about it like that, to make it like these are like functions. Okay? Okay. Now I want to talk a little bit about the schedule. So the processes are deterministic. Okay? They have a loop. They read a message. They do a deterministic function that updates a state, and so on. So the non-determinism in the system. So non-determinism, what that means is that if I start with a given initial configuration and I execute the system, then the two executions might be different, even with the same initial configuration, because the messages take arbitrary time. Okay? Processes execute at different speeds. So maybe the process is taking a long time and the message is taking short time, and maybe the message takes long and the process is short. So these times are arbitrary. So the asynchrony of the model shows up, so the asynchrony of the actual distributed system, shows up in the model as non-determinism. Okay? It shows up as non-determinism in the schedule. So the schedule, all we know is that each of these events is applicable here. But if M is in the outbuff of I, then this, and we don't remove M from the outbuff, this event will be applicable in many, many, many possible configurations. Okay? The dels, we can delay them. It's not because M is in the outbuff that we have to do immediately. We can do a comp event and another del event. So this del IJM, we have many possibilities for doing it. It can be delayed. Okay? So there's many possible schedules. So for a given algorithm running on a distributed system, there are many possible of these schedules, and so the system will actually be non-deterministic. And this is how real distributed systems work. In an asynchronous model, so this is actually modeling the asynchrony where the message travel time can be anything. So you can see that the processes, the nodes, the single nodes are deterministic, but the schedule introduces non-determinism. Because of the timing, there are many possible schedules for a given algorithm. When we execute an algorithm, we can have many executions depending on the time. And so we have different schedules. Okay? So the non-determinism is all coming from the schedule. It's coming from the timing of the messages and the computations. So you can see, even though we don't actually say exactly how much time, the millisecond or the microsecond of the messages computation, the timing shows up. It shows up in this fact that the dels can be delayed. Okay? So the non-determinism of the schedule is where we see that the system is really asynchronous. Okay? So you see that? So again, this is a modeling thing. Time, the asynchrony, so asynchronous system, the real system, it shows up as non-deterministic model. Okay? So the asynchrony in the real system is showing up as non-determinism here, even though we don't actually give the actual wall clock times. You see that? It's actually very intuitive. Maybe it seems abstract, I'm not sure. For me it seems very intuitive, but, and it's kind of the right way, because with this non-determinism, we can actually model all of the interesting things that the real distributed system does. Okay? When we start building algorithms like broadcast or consensus. So given the initial configuration, the schedule determines the whole execution. Okay? Now, of course, you can't just randomly put events here. Not all schedules are allowed. The del ijm is only allowed if m is in the outbuff of I. Okay? For example. Okay? Now, we can define a property called admissible executions. Admissible execution, it's exactly what fairness is in a concurrent system. So remember, you have programmed concurrent systems, right? You remember concurrency when you have multiple threads, and you have a scheduler when you have multiple threads. You remember that, And the scheduler, each step will pick a thread that it executes, and maybe it's using time slices or whatever, but it has to make sure that you don't have starvation. You remember that, Well, exactly the same thing, we have to define it in a distributed system. But a distributed system is a little bit more general. We don't just have threads, we also have messages. We have something extra. We have each process, which is like a thread, and it's running, doing computation. It's like a thread. So we don't want it to starve. So in the model here, we have to make sure that each process gets comp events regularly, so it doesn't starve. That's like starvation. But we have a little bit more. A distributed system is like a generalization of a concurrent system, because we have extra thing, which is the messages now sent between the processes. Okay? So each process needs to have an infinite number of comp events. So that's the fairness that you know of a concurrent system. Each thread, the scheduler has to give it infinite number of steps. So it can't let it starve. But we have an extra property here. Each message sent is eventually delivered. So we have the notion of fairness. We have generalized it a little bit for concurrent systems. And in concurrent systems, fairness is called admissibility. It's called admissible. Why it's like that? Well, that's the terminology, okay? So fairness in a concurrent system corresponds to admissibility in a distributed system. So it's a generalization, basically. Admissible executions are like fair executions. And it's generalizing because there's one extra thing in a distributed system, which is the messages, which don't exist in a concurrent system. So typically, in a concurrent system, you have all these threads. They're looking at shared memory. They're doing updates in the memory. So the information is being shared through the memory, but there's no send and receive, okay? In the current system, like in multi-core, there's no send and receive. Shared memory, and they're doing updates of variables. But in a distributed system, we have these messages. That's the new thing. So the messages also have to be fair. And that means that when you send a message, you have to eventually deliver it. You can't just let it hang around forever in the network. Okay? And it's interesting, the definition is interesting because we say each process has an infinite number of comp events. That's a nice way of defining it. It's very simple. So we assume all executions are infinite. Why do we do that? Well, it allows messages to wait arbitrarily long. There's no limit. If there would be a limit, then the messages could not wait longer than that. So there's no limit in how long the messages wait. So that's exactly the asynchronous model. No limit on how long the messages wait. But the algorithm might not take so long. Well, when the algorithm is finished, the algorithm is just making dummy transitions. Huh? So we need the infinity because the model is asynchronous. It means messages can take arbitrarily long, finite times. So if it would be finite, there would be a limit on how long the messages could take. But this limit does not exist in this model. That means that's why in the model, executions are infinite. Okay? So that's what an admissible execution is. Basically, it's fairness. Right? It means there's no starvation for the processes and no starvation for the messages. Okay? So that's pretty clear. So this model is modeling the asynchronous. This is modeling the asynchronous system. Now, messages can take arbitrary finite times. But last week we saw there's also another extreme, which is called synchronous system, where there's actually an upper bound. So we actually have to change the model if we want to do synchronous systems. So this model, for what I'm just showing here, is actually modeling asynchronous. It's the simplest, most general model. But in the real world, there's also synchronous systems. So we have asynchronous, and we have on the other side, we have synchronous. So this model, the model that I just defined, is for asynchronous. There's no bounds. And then with synchronous, we have to actually make some modifications to the model. So I will make the modifications to the model to show how it can model also synchronous execution. But maybe I make a small break first, depose. After the break, I'll talk about synchronous. Okay? So then you can meditate on this model for a couple of minutes. Let me explain now synchronous systems, the model for synchronous systems. So the model I gave you so far is for asynchronous. So to make model of a synchronous system, we basically have to make some modifications, but it's not so hard. We actually just have to add some constraints on the schedule. So not all possible schedules are allowed anymore, because in the old model the messages could be delayed for a very long time, the asynchronous one. But in the synchronous model, we can add some constraints on how the schedule is done. So we're going to partition the execution into rounds. So rounds are basically non-overlapping. Each round is a period where things can happen, and then we go to the next round, and so on. So we have one round to the next. So this is how we model the time bounds. Okay? So the model is not going to have the exact number, the exact time of the bound, but the existence of the bound will be in the model. Okay? So each round, certain things can happen. So every process can send a message to every neighbor. All messages are delivered. So each process can send one message to every neighbor, and it will be delivered in the round. And each process can do one computation step. So basically, one message between any two processes and one computation step can be done in each round. So that's the intuition. Okay, so each round will do one basic step of things. So formally, so the rounds are disjoint. So the round consists of a delivery event for every message in all out buffs. So all the out buffs are emptied, okay, in the round. And every process does one computation event. So everything moves forward. Okay? And in this model, every execution is admissible. Okay, there's not going to be delay because all the messages will be delivered and all the processes advance. Okay? So by definition here, by this definition, it's immediately true that the executions are all admissible in a synchronous system. We don't actually need that extra conditions. Consequence of this definition. Okay? So basically, we empty the out buffs, we do one computation event. So this computation event might do sends. Okay? It might put new things in the outputs, while in the next round, they will be delivered. Boom. Okay? So they sent in one round, delivered in the next round, and that's it. So the synchronous system is, so you can see it's basically a simple extension of the model we have here. It's just putting constraints on the schedule. So that's nice, okay? That means that most of the things we do in this model, most of the terminology we have, it's going to be the same for synchronous and asynchronous. It's just that we have this notion of a round that we had here. This disjoint rounds is a new thing, a constraint on the schedule. Okay? So that means pretty easily we now have a model for both asynchronous and a model for synchronous systems. Okay? Great. Now that we have a model, now let's start doing things, let's start understanding it. One thing now I want to understand is the notion of ordering of events, timing, order, causality.